Hello, everybody. Good morning. Welcome to this third webinar of the Fatigue4Light project. Today, we have a very important topic that we want to address. The webinar is focused on driving sustainability, eco-design, and life cycle assessment approaches for electric vehicles. Now, we have quite a busy agenda for today. Thank you for your attendance and for your interest in our work. We will begin the webinar with a general presentation of the Fatigue4Light project to let you know more details regarding the work that we've done in these past years. After that, we will have a talk focused on lightweight evolution, an eco-design methodology for reducing weight in electric vehicles and minimizing environmental impact, which will be given by Violeta Vargas, advanced researcher on environmental impact from EURECAT. We will continue with a talk centered on analyzing the life cycle of cobalt-free lithium-ion batteries, a sustainable shift in electric vehicle energy sources. This is a talk which will be given by a senior researcher in life cycle for energy technologies from IREC, Victor Jose Ferreira, and he will be representing the COBRA project. After that, we have a talk which is centered on charging sustainability in battery packs, a journey through life cycle assessment and eco-design. Talk which will be given by Jose Jorge Spi from EURECAT, Head of Sustainable Impact Line. He will be representing today the MARBEL project. And we will finish with the talk which is given as a recognition, let's say, of the Liberty project. The talk is titled Correlation Between Circularity Calculations and Life Cycle Assessment for Electric Vehicle Batteries, Influence of Key Battery Life Cycle Parameters. The talk will be given by Aitor Picatoste, PhD candidate from Mondragon University. Okay, we will finish with a brief session, let's say, a space which is devoted to questions and answer. If you have any doubts, if you want to know more about our work and what we do, we are here to answer. And the plan is to close the webinar at 11:30, so we won't steal more of your time. Okay, from my side, my name is Lucia Barbo, by the way. I'm the coordinator of the Fatigue4Light project. I'm an assistant professor at the Polytechnic University of Catalonia, UPC, and also at the International Center for Numerical Methods in Engineering, CIMNE. And without any further ado, let's move on with the agenda today. And let me share with you some interesting data, some interesting facts about the Fatigue4Light project. Okay, so I don't know if you know something about our project, if it's the first time you are attending a webinar related to the Fatigue4Light project or not. But let me just mention that Fatigue4Light stands for Fatigue Modeling and Fast Testing Methodologies to optimize part design and to boost lightweight material deployment in chassis parts. Now, we are closing nearly the project, so we have a lot of information that we want to share with you. And I will give to you a general overview of the consortium, of the project phases, what is the research that we've been pursuing beyond the state of the art, what are the materials, the lightweight materials that we focused on in the project for electric vehicle chassis parts. And after that, just a brief overview of the results we have obtained, because, of course, the time is limited. Now, regarding our project, Fatigue4Light is a Horizon 2020 project funded by the European Commission. We've started working in February 2021, and we are finishing actually at the end of this month. So we have a really busy month, and we are happy that you could join us for this webinar. The budget for our consortium is 5.5 million, out of which 4.9 was funded by the European Commission. And we have quite a big consortium. We are 13 partners from 4 different European countries. The coordinator is CIMNE, the institution that I'm representing, as I was mentioning, the International Center for Numerical Methods in Engineering. Okay. Now, regarding our consortium, who are we in the Fatigue4Light project? Well, we have a very varied consortium because we have research institutions, universities. The weight of the consortium holds with industrial companies, so we have quite a strong presence from industry. And we have one standardization body to help us promote the fast fatigue testing experimental methods that we have been developing in the consortium. Okay, now who are we? Who are the people behind the numbers and behind the names? You can see the evolution throughout the years as the Fatigue4Light project has progressed, and we are obviously, I would say, with every consortium meeting, we are more beautiful, more experienced. So, well, time passes for everybody, I would say. Okay, now regarding the Fatigue4Light project, how did we pursue the work plan during these 3 years? Well, we started with the first year, which was heavily focused on coupon behavior. Okay, so analyzing the performance of different materials at coupon level. After that, second year was devoted to adding more complexity to the problematic of fatigue behavior, and we studied this on a lab scale component, which exhibited several different manufacturing processes influence. Okay, and the third year was heavily focused on demonstrator level, so maximum level of complexity, where we wanted to showcase all of the developments that we've been producing these past 3 years. Regarding the workflow, we started by analyzing basic material behavior. Okay, so material performance, mechanical, packaging, performance. After that, we moved to the development of tools for lightweighting, and in this sense, we have developed in the consortium some experimental techniques which are specifically targeting fatigue testing, which is very time consuming. So we are looking to reduce this time. After that, we've also, I would say simultaneously, we've worked on developing fatigue simulation techniques to assess numerical simulation of under cyclic loading. And in the end, of course, we've reached the culminating point, let's say, or the maximum point of our project, where we want to exhibit all of these different techniques developed at the demonstrator scale, industrial scale. Okay, now what have we been pursuing in the Fatigue4Light project beyond the state of the art? You see, the approach that we wanted to see, obviously we are targeting fatigue, so we want to target chassis component. And already there are tools, numerical tools and also experimental tools, which offer service to the industry regarding these topics. But in Fatigue4Light, we wanted to have a comprehensive approach where we want to study the fatigue behavior of the materials, but taking into account also the influence that those manufacturing processes, which are typically used in the manufacturing of chassis components, they are taken into account because they induce geometries, etc. And these similarities, of course, affect the performance. Okay, so I've been saying that we've been studying these lightweight materials. Which specific lightweight materials? Well, we have 2 different advanced high-strength steels, the complex phase 800 and complex phase 1000, which have been studied. In the case CP800, in the case where it is not already used as current state of the art, and where CP800 is used, then we've passed to CP1000 to see what would be the change in the behavior. After that, we've had an important package of work focused on hybrid materials and stainless steels, which is here we have metal composite sandwiches materials, which have been developed. Press hardening steels also, specifically targeting heavy-duty vehicle chassis. And after that, we've also studied some aluminum alloys that have good fatigue properties. Okay, so a very brief overview of the results that we've obtained in the project. Okay, so as I said, the first year was focused on specifically the material performance at coupon level, and here we've had different types of tests that we've been analyzing. Of course, the tensile test, the local formability of each material, the fracture toughness, and also environmental effects through the corrosion test. And here you can see an overview of the comparison in between the different materials that we've analyzed in the project for each specific type of test. However, for us, the most important behavior, I would say, or test that we were focusing on was the fatigue behavior. And here we studied the fatigue performance from several different points of view. First, using the conventional staircase method, and after that, using 2 fast experimental techniques to accelerate the obtention of the fatigue limit and also the fatigue SN curve slope. And these were the self-heating method, which was proposed by ArcelorMittal, a part of the consortium, and also the stiffness method proposed by Eurecat. We've also studied the performance of the different steels through the very high cycle fatigue method, so ultrasonic fatigue, by means of the team at Polytechnic Auditory. And here you can see, of course, some overview of how the different materials performed in terms of the fatigue limit, for instance, and some information that you can follow, you can look up if you are interested in this fast experiment. Okay. Now, regarding the second year of our project, so results we've obtained at lab scale demonstrator level. Okay. Here we had a big campaign, which was done on this L-shaped demonstrator, and we wanted to leave some edges unpolished, some part was fully polished, and we checked the behavior and decided, of course, with a reversion factor of -1. And here you can see, for instance, also some video regarding the performance in the numerical simulation done by him. By the way, the results that we've obtained in comparison between the experimental and the numerical part, they were in very good agreement with the formulation we developed. Okay, now let's go to the most complex level, because this is where we have, let's say, the most spectacular results at demonstrator. So we have several different demonstrators in our project. I will start with the steel lower control arm, which was proposed by Fiat. And here you can see the parts as they were manufactured, and then the fatigue bench setup. This is the component after the misuse test, and here you can see a comparison between the actual experimental failure and the numerical behavior. And after that, you can see, for instance, for a fatigue case, how the crack propagation, the failure of the specimen, the crack propagation accompanying this failure has been developed in the numerical model as compared to the experimental model. This was a very complex case because we've had two different cracks, and there was a primary crack which began developing at the beginning of the simulation, and then secondary crack which finally broke completely the sample. Okay, let's move on. This lower control arm was also manufactured in a hybrid version by a metal composite sandwich laminate, and the manufacturing and the testing was performed by RISE, our partner in the consortium. And here you can see, for instance, a vision, an overview of the broken sample, the broken hybrid arm, and also how the test was performed and the evolution, let's say, of the mechanical loading. In this case, it's just monotonic loading. Okay, from Siemens side, we also simulated the behavior, and we noticed a good agreement in terms of force displacement between numerical and experimental. Now, I want to show you a video which was promoted by our colleagues at RISE. Let's see if I can do it well. I think here. Okay, for some reason I can't manage to put it on, but the good thing is we have this link over here that we can click, and it will take us to the YouTube video. And I can show you great work done by the team at RISE regarding the manufacturing of this specific hybrid arm. I don't want to spend too much time, so you can find the video. You have the link in the presentation, and you can find the video online. But let me just show you how the tool was manufactured for stamping and pressing this arm, and how the arm was finally built. It's a very interesting and beautiful process, I would say. But just to say that we've had an intense numerical simulation campaign before the actual manufacturing of the arm to determine what were the hotspots that we had to eliminate, let's say, from the geometry or correct. Here you can see how the arm was manufactured and stamped. You can see the identification of the hotspots, and also the hybrid forming, where this aluminium outer layer have been glued to this inner composite part, which was made with glass fibers, and actually everything was joined together. And here the final version. Okay, so let me go back to the presentation, and I will go very fast. Okay. Another demonstrator that we've had in the project was a disc prototype for a wheel, which was proposed by Magneto Wheels, another partner in our project. And for this specific demonstrator, a new stamping cycle was developed for the CP800, which was a new material which they wanted to investigate. And some interesting results were seen. For instance, that this stamping process for the CP800 led to diminished fatigue properties as compared to the DP600, where in turn the stamping process led to improved fatigue properties, which is curious. Here, just an overview of some simulations and how they compare numerical with experimental. Okay, another demonstrator that we had for heavy-duty chassis, which was the cross-member beam proposed by Gestam. Here you can also see a video of the manufacturing process. This is a symmetrical design, so we manufactured the beam, and you can see the setup for the monotonic test and afterwards for the cyclic test. This is the monotonic comparison between force and displacement, and this is an overview of the fatigue behavior. So we have a cyclic case, and you can see that the crack has developed at about 70,000 cycles, and in the simulation, the crack also started to appear at a comparable. Okay, these were the demonstrators, and what I've spoke to you about so far was the mechanical behavior. But what about the eco-design assessment? Because we are very interested in seeing how these different materials that we've analyzed in the project compare also from different points of view. So recyclability and weight reduction, CO2 emission reduction. So from this point of view, the next talk given by Violeta Vargas from UNECAT will target specifically this part. So without further ado, let's move on.
I think you can see my screen, right? So I'm going to talk to you about what we've done within the project, as Lucia was saying before, about what we've done on eco-design. We developed a methodology and we applied it in Fatigue4Light, and we also have some results from the environmental point of view, and I'm going to show you just a few of them. So, I'm sorry, wait, just 1 second. I don't know. Okay. Sorry. Okay. So we developed a methodology for applying eco-design in different projects. And this methodology is very simple. It follows 4 simple steps. It is plan, do, study, and act. And then these steps were adapted to the different projects that we've been applying it to. And in this case, we have these 4 steps. The first one is to find the hotspots, like where is exactly the environmental impact or the greatest environmental impact in the life cycle stages or in the different steps of it, of the development of different technologies. Then the second step would be to find the different strategies that we can approach to find a better design that follows a more environmental perspective. Then adapting these strategies to the technological aspects and procedures. And at the end of this, define a set of eco-design specific actions for the project and put them in, well, set them in the development of these demonstrators. So I said it very fast, but and I'm going to just give you a few hints on what we did in Fatigue4Light, but then Jose is going to explain more in detail what is the methodology and how is it applied. So in Fatigue4Light, we applied the methodology at the first step. We found some hotspots. We figured what were the steps that were actually with more weight in environmental impact. And we developed this sheet. Well, it's like an Excel sheet where we have an impact range for the different life cycle stages with the different impacts, the greatest impacts in the different life cycle stages. And then following this, we could focus on the more important aspects of the development of these demonstrators. So in this case, to develop the strategies that we were going to follow through the project, we were focusing mostly in lightweighting alternatives. But we also focused on maintainability, lifetime extension, in recycling at the end of life, in the content of critical raw materials as well, and second market resources as well. So we did an evaluation of these different strategies that we developed within the consortium, and we saw where these strategies would have the greatest impact within the life cycle stages that we were considering for the project. Then we have this table that is like a summary of these different strategies and the description of each of the strategies. So now we know where to focus, but we have to make sure that the strategies are also aligned with the technical procedures and aspects of the project. So then we moved on to step 3, where we make sure with the team from the consortium that these are actually applicable, that are viable from an economic point of view and also from the technical point of view. So some of the strategies were disregarded at the end, and then others were added or modified to make sure that these are aligned with the project and with the feasibility of them. After that, we developed a set of specific actions for Fatigue4Light, and then we evaluated these actions through a matrix score based on analytical hierarchy process. For that, with the result, we did this methodology. What it does is, in a group of experts, we graded these actions as how important they are and how easy they are to apply. So we gave them a score, and we figured which one was the most important for the Fatigue4Light project, and then we ordered them as this ranking. Then after that, now that we have the methodology, we have to apply it, and we have to make sure that we are actually getting better results after applying the methodology. And to make sure that we are doing the right thing, we needed first a preliminary assessment at the beginning of the project, or a baseline assessment of what the technology is in the market right now, and then compare it to what would be applying all of the strategies and actions that we defined with the eco-design methodology. So just a little bit on the life cycle assessment part, we did this system boundaries. We considered the life cycle assessment from the beginning of extraction of raw materials, then all the manufacturing of semi-finished products, auto parts, and also the assembly of the vehicle. Then we consider the use stage of the vehicle, and I'll show you a little bit on what were the considerations for the use stage in a moment. And we also considered an end of life that is like the current end of life right now, or a functional unit of 1 kilometer that has been driven by an electric car, or a hybrid, or a plug-in, different options of vehicles. So for this, as I was saying, we considered a lifetime driving distance of 180,000 kilometers, according to a report from the European Environment Agency. And also in this report, they state how much these different vehicles consume in terms of fuel and energy for the different types of vehicles. They also have like different kinds of like ranges of vehicles, like small or more or bigger cars. But we did an average number for each of them. So applying this, we came up with this result that is a big improvement for all of them. And I'm just showing global warming potential for each of the demonstrators. Here you can see the lower control arm, the crossbeam member, and the wheel. You can see that they all improved in the Fatigue4Light solutions. Some of them are more evident. For example, the crossbeam member is a 31% reduction in carbon footprint, considering all life cycle stages. And we can see how the production may have more or less the same impact, but then if we reduce the weight of the vehicle during the lifetime of the vehicle, and considering all this use, as I was saying, the consumption of energy and fuel during the lifetime, then we have a reduction on carbon footprint during the lifetime of the vehicle. Here you can see only the results for the battery electric vehicle, but we have the results for all the other different types of like combinations of vehicles. Then we have the lower control arm that you can see that is like, it seems low. The reduction is the 7% in carbon footprint, but it's actually a lot higher if you consider all the other environmental impact categories. In some of them, in some cases, it's up to 65% of reduction of impact. Then on the case of the wheel, we have a reduction of 24%. And we can also see a bigger reduction in other environmental impacts, such as resource, like abiotic resources are reduced in as 57%. In all the cases, we can see the impact during the use stage due to the reduction on the weight of the vehicle and the consumption through the lifetime, the use time. So the conclusions of applying the eco-design methodology is that this methodology allows to a better teamwork to participate in all the decisions on the process of designing better demonstrators. This methodology also allows to enhance the implementation of different technologies and procedures that cover all the life cycle stages of a product. This methodology also addresses directly the environmental perspective in a continuous way. It also allows to obtain valuable inputs from the partners that we can align the strategies and actions to make sure that this eco-design are viable and applicable. And we obtain a ranked list of actions through the application of analytical hierarchy process that all the partners were participating in. And that would be it from my side on the part of eco-design.
Great, thank you so much, Violeta. Okay.
Yeah, that.
How do I stop sharing? I don't know. Well, thank you. And let me go to the overview for today. Okay, we can proceed with the next presentation. So I will leave the floor to Victor Jose Ferreira from IREC, senior researcher, as I was saying, in life cycle assessment and life cycle cost for energy technologies. The talk is focused on analyzing the life cycle of cobalt-free lithium batteries, a sustainable shift in electric vehicle energy sources. Okay. Go ahead, Victor, with sharing your screen.
Hello, everyone. Thank you for this invitation and participating in this webinar. I will share my screen. Okay, my name is Victor Ferreira. I am in charge of the lifecycle assessment and sustainability of the energy technologies in the Catalonia Research Institute for Energy. And I will present you an overview of analyzing of the lifecycle cobalt-free lithium-ion batteries for sustainable shift in electric vehicle energy source in the context of the COBRA project. This is the outline that I will present you today. I will give you an overview of what is the role of the CO2 equivalent emissions versus the impact of the critical raw materials in the electrical vehicle energy source, which is the importance of the cobalt-free lithium-ion batteries in the renewable energy transition in the context of the electrical vehicles, the current challenges in adopting the cobalt-free lithium-ion batteries, and I will present you some results and the LCI studies for the COBRA project, focus on the development of the solutions in cobalt-free batteries. Yeah, we know that the electrical vehicles plays an important role in the energy transitions in order to reduce the emissions related to the fossils. But it is important to remark that there are other environmental implications more related to the resource depletions or use of the minerals or key metals or as critical raw materials, for example, cobalt, nickel, manganese, and graphite. These materials can bring environmental impact throughout the battery supply chains. So that is why that it is very important to address the life cycle studies for these electrical vehicles focus on the electrical and battery value chains. We know that, for example, the cobalt and nickel are the main element uses in the batteries, and if we explore the next European battery production, we know that until 2030, the production of the electrical vehicle will increase. So this implies that the environmental impact associated to these metals should be significant in the environmental footprint. Other important aspect that we can analyze is, for example, in the cobalt, is the social aspects. We know that the mostly amount of this metal to produce the batteries coming from of the Democratic Republic of the Congo, well, in this area there is a lot of problems, geopolitical problems for the extraction of this metal, and more focus on the child work, safety meaning conditions, and this is very a problem that we have. So this is why it's important to reduce or create batteries without cobalt, but we know that we have to maintain the performance of the batteries in the electrical vehicles because if we explore the current challenges in adopting the cobalt-free lithium batteries, when we know that the cobalt allows us to have the good energy density, but if we reduce the quantity or eliminate the cobalt in the batteries, we could have a lower energy density. Another parameter which is very important is the stability that cobalt can provide the batteries as well. On the other hand, if we reduce the costs by eliminating of the cobalt, it implies to use higher amount of the nickel as alternative, and can be expensive due to its rising price. So these are the main challenges in adopting of the cobalt-free lithium-ion batteries. So this is why projects like COBRA, which is a European project funded for the program Horizon 2020, can bring some studies and developments in order to overcome many different shortcomings faced by the electrical vehicle batteries in order to create this is kind of the cells without of the cobalt. In this case, the COBRA project is focused on the lithium nickel manganese oxide cathode in combination with other composites in anode based on a nanometer silicon and graphite and active particles. So there is other solutions or developments in the COBRA project in order to overcome these challenges that I explained in just a moment, in order to have a good energy density, low cost, and increase the cycles and reduce the critical materials. And the other aspect or other activity very important, which is in charge of the IREC, is the performing of the life cycle assessment, and in order to explore what is the impact, environmental impact, when we reduce or eliminate this metal from the cells. And other aspects that we are exploring is the recycling aspects and the second life application evaluation. So it is only to say that there is a good consortium in the COBRA project from the different European countries. IRE is the coordinator, the coordination of this project. The project is expected to be finished in this year, at the middle of this year in June. And yeah, we expect to have a good results in order to overcome these challenges. Well, regarding the life cycle assessment of the lithium-ion batteries, I want to only refresh something aspects. For example, this methodology can bring us the holistic procedure to evaluate the environmental impact, which is related to the new methods, for example, the product environmental footprint, which is aligned with the new European regulation for the digital battery passport. So there is a different key parameters, scopes, and data, which is a challenge for the persons which develop the life cycle assessment. There are a lot of functional units in the life cycle studies, but according to these recent methods, the functional unit which it uses is the 1 kilowatt hour for the total energy delivered or capacity during the battery system service life. Other parameters is very important to be account is the scope. We can do analysis from the cradle to grave, cradle to gate, including the raw material extractions and processing. This is for the cradle to gate, but if we include the use phase and the end of life, we are analyzing the cradle to grave approach. We have to face different other aspects. For example, the lack of the harmonized data in the uses phase. The life cycle results are influenced by the electricity mix of the country in which the batteries in the electrical vehicles is charged, and the efficiencies and losses, etc. On the other hand, the end of life stage can have a lack of the data, because this is important to characterize the processes for this dismantling phase and the different recycling methods, for example, pyrometallurgic methods, hydrometallurgic methods, and direct recycling. This is our emergent technology for the recycling, and there isn't enough data to characterize this. And the other aspect is to include the circularity, consider the credits of the recycling in the LCA models. And the other aspect is not only to focus on the carbon footprint indicator, because there are other environmental indicators that we have to pay attention in order to have a holistic environmental impact assessment. I want to only show you in the life cycle assessment from the cradle to grave approach, mostly of the LCA studies tell us that the production stage has the higher environmental impact. You can see in this slide the total production and the materials can bring a range since 61 146 kilograms of the CO2 equivalent per kilowatt hours of the battery capacity. The other hand, the life cycle, the end of life can have 12% of the GHG emissions of in the lithium-ion battery. So this is some figures, but the important point to say here is the production stage. If we consider in the end of life for the charging of the vehicles, renewable energy, this implies that the production stage has the higher impact. So if we go to the cradle-to-gate approach, we can see that the battery cells through all environmental impact has the higher contribution for the different lithium-ion batteries. That is why we can start the life cycle assessment from the cradle to gate, focus on the cell level when a project like COBRA is investigating about the different chemistries without cobalt-free batteries. In general, we are doing we are following the life cycle assessment methodology, defining the goals and the different functional units. We can start for a kilogram of the material of the cells for the cradle to gate approach, and the kilowatt hour of the energy deliverable in cradle to grave, and we consider the reference flows through the first life and second lives. The more critical stage is the life cycle inventory. We are consider the background data using EcoInvent and the Sphere Gavi data sets. For around data is supplied for the developers in the project, in the COBRA project, and we use specialized literature and specific softwares and different assumptions. So there are, as I mentioned before, there are a lot of environmental impact indicators, but I will focus in this presentation on the climate change and the global warming potential indicators and surplus or potential, which is related to the category of the mineral resource scarcity. So these are the preliminary results for the cradle to gate of the COBRA studies. We can see for this indicator for in terms of the kilograms of the copper equivalent per kilogram of the cells, we can compare the conventional NMC 622 cells, for example. When we compare this cell with the COBRA solution, there is an important reduction in this indicator, and this is attributed to the absence of the cobalt in the COBRA solutions. If we see the CO2 equivalent indicator or carbon footprint, we have a similar result. The reduction of this indicator in the COBRA cell is very important, and so this tell us that what is the important strategy to try to create the battery without cobalt, because this is environmental metrics, for example, are very reduced drastically in this kind of the batteries. This is good reduction in order to reduce the environmental impact, can confirm that the creation of the cathode chemistry for the lithium-ion battery without cobalt. Other activity that we are doing in COBRA is to performing the environmental hotspot analysis from the life cycle assessment, from the results of the life cycle assessment, in order to create the eco design guidelines. In IREC, we are using standards for the eco design in order to create our own methodology for the eco design guidelines. In this approach, we define the life cycle project parameters, which are divided in modifiable parameters and non-modifiable parameters. The modifiable parameter allows to the engineer and designer to make some strategies for sustainable designs. And the results for the life cycle assessment allow us to have these 3 score ranges of the score in order to put these scores in the different life cycle stage parameters and throw out the different environmental impact that we are evaluating. In this case, the engineer or designer, if the engineer or designer want to evaluate the life cycle stage, the engineer can focus on a particular environmental impact, for example, global warming potential, and so what is the higher score throughout of this parameter. But if the engineer wants to concentrate its strategy in a particular material or aspect of the life cycle stage, in general way, can address or consider the different scores which is involved in the different environmental metrics. So yeah, this is all from my side, and that we are doing in the COBRA project. And yes, for some questions at the end, we can address this.
Okay. Well, thank you very much, Victor. As you mentioned, we will have some dedicated time after all the presentations, about 10 minutes or maybe more if we need, for questions and answers. So if you have any question for any of the speakers in this session, please write them in the chat and we will address them. Okay, now to move forward with our agenda, we have to speak now, or I have to give the floor to Jose Espi, representing the MARBEL project. Jose is the head of sustainable impact line at Eureka, and his talk will be focused on charting sustainability in battery packs, a journey to life cycle assessment and eco design, the case of MARBEL Horizon 2020 project. Jose, go ahead, please.
Hello, thank you so much. Welcome everybody, and good morning. I guess that you will enjoy my presentation regarding the MARBEL project. MARBEL, as it's an European Horizon Europe project focusing on the manufacturing and the assembly of innovative modular and reusable battery for electric vehicles, aimed to introduce the environmental friendly and the lightweight solutions on the on this battery concept. Regarding that, and I think that it's a little bit recurrent with the main statements of the previous colleagues that have informed about the options on the innovative electromobility. I think that right now we have an increase on the CO2 emissions that are very linked, for example, on the gross domestic product, but we will have to reinforce the vision about the importance of the transportation and storage sector that allows more or less the 11% of the total CO2 emissions of the world. In that sense, it's really relevant that we could provide some solutions to try to decrease drastically these emissions. And what exactly in terms of the battery pack we have already noted that, for example, the weight of a typical battery ranges about 450 and 900 kilos. And regarding the materials that are already included, some of them, like for example, are lithium, it only covers 8 kilograms, or even cobalt ranges about 14 kilos, or even the use of manganese that are around 20 kilos, are more referred
Jose, I think we lost your microphone because we can't hear you any longer.
meantime, for example, yes?
Now we can hear you. It's perfect. Go ahead.
Okay. I was muted, or? Okay. Well, I follow with my presentation. Around 25 and 40% of the rest of the different components of the battery, the metal casing, cables, the thermal management system, or even the battery management systems, it ranges from 25 until 40% of the total weight. In that sense, what was the main aim of the MARBEL? Trying to focus the different actions without having into account the nature of the cells, trying to determine, well, to conceptualize and manufacturing innovative vision of a modular, reusable battery for electric vehicles with some specific goals, trying to decrease in a 20% the weight of the total battery, to trying to reduce as well around 25% the charging time of such battery. By the different improvements, trying to extend the battery life up to 300,000 kilometers, to try to conceptualize an easy and safe disassembly automatization, and or even trying to perform some improvements on the repairability, the second life transition, to trying to adapt the cells and vehicles, and focusing on the more or less that such goal more related to the webinar of today, trying to improve the life cycle perspective of the battery by reducing their impact in around 40%. Okay, in that sense, we have what we trying to implement on the MARBEL project. We have a division or trying to reduce that impacts, but as well at the same time trying to determine what are the links between the technical procedures of the project and on the different life cycle stages that we will trying to address. In that sense, by a cycle regarding the different hotspots identified, the strategies linked to that, the readaptation needed, trying to link the technical perspective with the environmental one, and the definition of specific actions, we tried to apply the methodology already more or less introduced by my colleague Violeta on the Fatigue4Light project, another one that are more linked to that such electromobility. This methodology has 4 differentiated stages, and in the step 1, we try to identify such hotspots regarding the life cycle, the different life cycle stages of the battery, but by the application of a benchmark analysis on the different conventional products, stages, and materials linked to a conventional battery, with the application for sure of the LCA and LCC methodologies in a simplified and a preliminary manner, trying to provide some feedback on the different project action and tasks, but not only by this application itself, but through an extensive compilation of different previous studies that will help us to try to determine an excellent starting point and the consolidation of this prior knowledge acquired. We define it in that sense different easily and understandable sheets that could be provided to the different project to the different partners of the project, trying to explain them what were the main hotspots and issues linked to different life cycle stages that, for example, in more detail here on the raw materials extraction and the components manufacturing, and an impact range by covering different batteries already developed in the past, that we more or less defined it at 30 or 50% of the total impact on the battery. What was the second step? The second step was the definition based in that hotspot analysis in a different co-design strategies in a very, very generic way. For example, the application of design for maintainability strategies, the lifetime extension of the battery, the use of different substitutes for critical raw materials, the consideration of second market resources, a portfolio of different strategies that, once again, was deployed in an Excel, not in an Excel, in different sheets, easily understandable by the different stakeholders between the project, trying to focalize what would be the different benefits of the strategies itself, what will be the relevance regarding the different stages, for sure, what will be the benefits from the environmental perspective, but as well from the cost one, a description of each strategy, the different innovative challenges that we will need to be overcome at the end of the project, and finally some different conclusions that allowed them out, or at least inspired the different partners trying to elucidate how these different strategies could be applied in our project. And this will be a key part on the project, because at the end we will try to align the different technological perspective, the different technological procedures already more or less deployed or conceptualized in the proposal phase of the project, by trying to link that environmental perspective. In that sense, this third step will be dynamized by the application of several workshops, where all these different strategies and the different technological procedures of the whole consortium will be put in common, and trying to determine what would be the different synergies and the different ways to proceed to trying to cover all these different eco-design strategies, focusing on, for example, the effective material usage or the effective material usage in terms of the nature and so on. But at the end, and the fourth step, to determine a set of different specific actions that will be embedded with the lessons learned from the environmental perspective about what will be the best generic strategies to be deployed, that overcome in a set of different specific actions with certain relevance. Here you can be highlighted the most prominent on the application of the MARBEL project, the use of recycled and recyclable materials and the extrusion of the different aluminum profiles, or the reduction of copper material needed for the electronic components by the application of different strategies allowed to minimize the use of such metal, or even the introduction of, for example, weldless connection to the cells that allowed us to support the disassembly repairing options. All those different actions that nowadays are being implemented, and for that reason, we will not have already now quantitative results, will allow us at the end of the project, by the application of such actions on the different life cycle stages, in a minimization of this impact by the help of, for sure, of the life cycle assessment methodology, and by including, for example, different perspectives from the cradle to grave, when we will try to analyze what will be the impact of the release of 1 kilowatt hour of energy during the lifetime of the battery, but as well by including different strategies on the second life, by the application or by including by elucidating the impact by kilometer, trying to figure out the different conclusions and the results of the application of the life cycle assessment. In that sense, we understand that the most hardened power of the methodology itself is that allow us to quantify in a very transparent way the different effects and process of the products on the environment, because it's a very prominent tool that allow us that by different by the support on that methodology, on that co-design methodology that I've already presented, that try to identify and prioritize what are the different elements with the most environmental impacts, and for sure for further improvement, and that allow us to develop robust and numerical supported impact reduction plans in for example, on the exploitation of the battery itself, on the different technologies emerged from the development of the project, and that at the same time allow us to reinforce all these different communication and reporting actions aligned with, for example, different standardized methods. Regarding all the different results already recovered from the application of the MARBEL project that it's ongoing, and it is expected to be finalized next year. For example, we have already defined very well the different concepts related to lithium batteries in electric vehicles. The material selections, the weight considerations, the electrical composition, or even the vehicle lifespan, or the saving derived from the reuse of such batteries, and the recovery of the different valuable elements are for sure key environmental concerns that have to be improved. And in a more abstract conclusion, we have already pointed out that the collaborative eco-design approach can lead to a more sustainable, efficient, and cost-effective solutions. Because at the end, if you have the chance to put in common the technical perspective and the environmental one, that more or less is not that easy work, and in this kind of different projects or proposals, it's very concerning. In that sense, the designers can identify and motivate the environmental impacts at the stage. It allows to choosing materials with lower impact and with energy efficiency, or even increased recyclability, and finally to obtain a more eco-friendly battery pack. And even on the foster innovation, or on the collaborative perspective that can facilitate development of strategies, not only on the battery packs itself and the potentially extension of their lifespan, but even in the own day by day of the different companies and so on. And that's all. Thank you so much. I don't know if you have questions or even we can perform them at the end of the webinar.
Thank you so much. Thank you so much, Jose, for speaking perfectly to.
You're welcome.
Also, yeah, I would say let's address any question after the last presentation in our session today. Okay.
Okay.
Okay. So then, the last talk that we have programmed for the webinar today is a talk given by Aitor Picatoste, PhD candidate and Liberty Project partner, with a talk which is titled Correlation between Circularity Calculations and LCA for Electric Vehicle Batteries, Influence of Key Battery Life Cycle Parameters. Okay, Aitor, so the floor is yours. You can share your screen.
Yep. Hi, guys. I hope you can see my screen. I'll just put presentation mode.
We can see your PowerPoint window. Okay, now the full screen. Perfect.
Yeah. Okay. So thank you, Lucia, for the introduction, and also thank you for inviting me to the webinar. I hope I can keep it up with the interesting talks, because my colleagues were quite nice in their presentation. So about the this was a bit of delay. So I'm Aitor Picatoste. I'm writing my PhD thesis regarding the circular economy and LCA of electric vehicle batteries. So this talk was quite interesting for me. Also, I'm part of the circular economy and industrial sustainability group of Mondragon Universitatea, where we look at the different industry products, and we try to eco-design, just then build maybe sustainable business models with this knowledge. But I'm here on behalf of the Liberty Project, which is an H2020 project from the European Union. And the goal for this project was to develop an innovative battery, which has, in my side, an improved sustainability performance, but also more autonomy, so range, also lower charging time, more lifetime in general, and also being definitely safe. So how this is going to be calculated within the project is going to be comparing the Liberty battery pack with a previous battery pack from our OEM. And the goal is to have at least a 20% improvement in life cycle environmental impacts in this new battery compared to the old one. So from Mondragon, our first natural question was, how can we achieve this improvement in the battery? And this presentation is kind of a response of what we got. For this, what we first did was to analyze what was the state of the art of different batteries. So this is not the battery we were using in the project, but just kind of a benchmark of what batteries were in the market. If you look at these batteries, you will realize that the inventories we're getting, they are fairly old. But this is what it's one of the issues with LCA is the data availability. So this you guys will know. So we used, again, we went to see the most market dominant batteries, which are nickel, manganese, cobalt, NMC. And this was based on the Ellingson et al. Paper from 2014. And the LFP, the lithium iron phosphate battery from Majuvetes and colleagues in 2011. These two batteries, you can see here in the table, they are fairly similar. The Majuvetes proposed a method where we could compare them, so we just followed that one. And we also applied the two dominant recycling methods in Europe, the pyrometallurgy method and the hydrometallurgy method, just to understand where the technology lied in terms of environmental impacts for electric vehicle batteries. So here, and coming back to the name of my talk, key parameters, here you can see some key parameters already. So the chemistry of the battery cell, also the recycling method, and then the energy efficiency, the lifetime distance, so the longevity of the battery, and just adding a bit more to this. Okay, adding a bit more to this, we went and added some other parameters, but these parameters, they were not so documented in the literature. So what we did was just to add some extra parameters in asking ourselves somehow, what if the longevity was longer? So the battery lifetime extension parameter was a response to this. Or what if the energy efficiency of the battery was improved? And we kind of went in the literature and made reasonable assumptions on how these parameters could be improved, just to then go back in the project and define what would be the best way to improve the sustainability of the battery within the project, right? Because we had the opportunity of being part of an innovative 100% new development. Going back one slide, so this was the scope we had for the battery. As I said, we had the opportunity to kind of act in every step of the life cycle, and therefore this is what we analyzed for both for the project and also for this previous assessment. So of course the raw materials, the battery manufacturing, use phase, both the electricity needed and also the efficiency, and the end of life management, which as you can see, it's a big part of the definition of the LCA, because we've got first the cell chemistry difference, and then going either through pyrometallurgy or hydrometallurgy. Then the rest of the components underwent kind of a more standard recycling procedure for their materials. So let's say aluminum, steel, even copper. Just there are more mature technologies to recycle this, and we awarded credits for the recycled material. So this kind of to convey how we approach this calculation. Okay, these are the parameters again, and regarding a bit more detail on how we calculated the LCA and how we added the circularity, because this is another thing I would want to be talking about. But regarding the LCA, so the functional unit selected was 1 kilowatt-hour of energy delivered by the battery. This is quite an interesting functional unit because it covers all the life cycle of the battery and maybe additional life cycles. And this is also the functional unit that it's the European regulation. It's just setting this for calculation of electric vehicle battery LCAs. Also, as I said, the credits are provided with avoided burden. And just to highlight the twofold dimension of the LCA for electric vehicles, what we highlighted here, we did obviously a complete LCA, but I am highlighting here in this presentation the global warming potential, because it's the standard category, and also the abiotic depletion potential of minerals, which is kind of one of the critical aspects of electric vehicles in terms of raw materials, the material needs, etc. In this regard as well, we added some circularity indicators and circularity calculations to this analysis, just because we see how the European Union is tending towards circularity in terms of strategies to be implemented, also just the circular mindset when defining some requirements for products. So we just naturally are including the circularity calculations to all the LCAs we're performing within this project and also in other projects. So for this, we chose the product circularity indicator, which is quite a complete indicator, analyzing every stage of the life cycle of the battery. And also, as a comparison, we also calculated the circularity index from Coolen, which is a very simple, streamlined indicator that only accounts for raw materials and the recycling. So this is kind of two different approaches to circularity that we're also trying to implement in our calculations. And with this, I think I go to the results. So this is kind of all the combination from the previous slide. So the global warming potential, the abiotic depletion potential, and both circularity indicators. We merged for this presentation. I merged them all in a same graph just to have a nice discussion with these 4 graphs in here. So as a bit of an explanation, first, just realize how the y-axis is the circularity. So the more up a point is, the better the circularity score was, and you can see how the circularity index is up in these 2 tables, and the product circularity indicator, a bit more complete indicator, it's in the 2 bottom tables. Going to the x-axis, we've got global warming potential savings and abiotic depletion mineral savings. And again, the more right you go, the better the result is. So that's why we're working with savings, which is not the usual way we report LCA impacts, but just to have a more natural understanding of the table, we presented things like this. And so a bit about the results. First thing first, you can see how the lithium iron phosphate batteries are grouped in the worst area of the graph for every combination of indicators that we are analyzing. Even if it's pyrometallurgical recycling, hydrometallurgical recycling, even considering maybe improved recycling or improved energy efficiency, it lies bottom left of the graph. A bit better, it's the nickel, so NMC battery with pyrometallurgy. You can see how both the circularity are improved and also a bit more savings. The best overall results are for nickel manganese cobalt battery, just in circularity, in any type of savings. And then I'm going to come discuss this. Also, of course, if you extend the battery life, there are some savings as well. And finally, and this is kind of surprising at first, but then I'm going to be talking a bit more about it. We've got the battery life cycle extension for the LFP. So LFP, it's considered to be severely underused now. So the battery lifetime extension assumption we made was just doubling the lifetime. And here you can see how still the results are mixed for LFP. For the circularity index, the savings are not as big. So you can see here that still it's in the bottom, even if the both global warming potential savings and abiotic depletion savings are quite high. But the other circularity indicators, so the more complete circularity indicator, yes, it considers this lifetime extension as very interesting for the LFP battery results. So all in all, and just as in lesson learned from this graph, the NMC battery, as it stays and considering state-of-the-art parameters, it's the best performing one. And the longevity of the battery right now, it's not very well accounted for in literature. Coming back to the other aspect that we are calculating, so whether the circularity and this circularity aspect pushed by the European Union is adequately measuring the savings or the environmental impact of electric vehicle batteries, at least. Here, I just cleaned everything out, and here you can see how for some of the circularity indicators, you cannot guarantee that an improvement in circularity measurements generally reflect an improvement in environmental impact. But this is not maybe so related to the circularity mindset, but to the metric. Because if you go down here and you take a bit more of a complete metric, you can see how, yes, a better circularity result provides environmental savings. However, and this is a disclaimer, it's not proportional. So maybe you can have a 10% circularity improvement, but you're saving only 2% of impacts, or vice versa. You're only having a 10% of circularity improvement, but you have maybe whatever 45% of environmental savings, depending on the category. So, as a conclusion for this work, this is something I already outlined it, but some numbers. So, NMC battery is the best battery. In average, they had 7% less global warming potential impacts, and even a bit more impressive, 20% less abiotic depletion potential of minerals impacts compared to the LFP. And also the higher recycling ratio, so maybe recovering 65% more mass in average, both in pyrometallurgy and hydrometallurgy, even if hydrometallurgy is a bit better resulting. Also provided a better circularity results, which feels natural, right? But it's important to have those numbers. Also, other two conclusions we took from here is that carbon emissions, they're not adequate to measure the complete sustainability of electric vehicle batteries. So here, I'm going to just come back for a second. Here you can see that for the results, the abiotic depletion potential savings are very far, and the scale is almost 50% here, while the global warming potentials are around 15%. And coming back to the numbers, so maybe the savings for some parameters are 7% in global warming potential, but it can go 20, 25, up to 45% in other categories. So this is important, and that's why I try to highlight the carbon tunnel vision here in the image, because we need to be looking at something else and not only carbon footprint. And also, coming back to the circularity and environmental savings issue, yes, complete indicators as PCI, so a very detailed indicator, could be used as a proxy for environmental savings, because we've seen that a better results in PCI tend to mean a better results in terms of LCA impacts, but they are not proportional. So as I said before, you could be implementing some measurement that it's not as good in circularity as it is in environmental savings. So for a proper analysis, you could start with circularity, but you always need to be going to the complete LCA analysis. And regarding the key parameters, as you can see, and this is not in the conclusions, but as you can see in this spot, the longevity is the actual parameter. So having the battery more time in operation, it's the actual parameter that it should be pushed forward in every technological improvement that we're looking. So either better thermal management, or trying to improve the battery charge discharge effect when going in fast charges, etc. Those kind of aspects are the ones that are key to be pushing forward in the future for a more sustainable battery. And yeah, I think this is all. Yep. Questions or discussion? I think we're going to have a dedicated slot for this. So thank you very much, and I'm just gonna stop sharing now.
Okay, thank you very much, Aidar, for a very thought-provoking, I would say, end of your talk with some very interesting conclusions. And at this point, we are going to conclude the presentations for our webinar. So this is the moment to write any additional leftover questions that you may have. From my side, I would like to ask all the speakers to please turn your camera on, so we can see you and we can interact in a, I would say, friendly way, right? And let's look a little bit at the chat, because we have quite several different questions here that are very interesting to address. Let me begin above. Okay. Okay, so we have a question for Violeta here, representing the Fatigue4Light project. How does the methodology address objectivity? Violeta.
Yeah, it's been challenging for us to come up with an objective way of assessing all the different strategies and actions within the design for circularity or eco-design methodology, because we could come up with 1,000 different actions to apply within the project, and then how were we going to apply them, like in order of importance? If we only considered our perspective, then it would be one result. If we considered the perspective of technicians or managers, it would be a different one. So we did different webinars scoring the different strategies and actions in a group manner. And then we came up with a score for the whole action from all of us, so that we make sure that it was a viable thing in terms of technical aspects, also in economic aspects, and that we were all agreeing in this different score. So I think this methodology, within the eco-design methodology, we apply the analytical hierarchy process that allows us to put these values to subjective matters or non-quantitative matters into numbers, and this is how we did it.
Okay, cool. Thank you. If you have follow-up questions, okay, after the answers, please also add them in the chat, okay? Now, the next question that I have is also for you, Violeta, regarding the GWP. You showed regarding the wheel. Does it consider 1 or 4 wheels? And how is the impact of the use phase calculated?
Okay, so what we did is we considered 1 wheel during the whole life cycle of a wheel in an electric vehicle. And for the results that are shown in this presentation, it's only battery electric vehicle. And for this, I think the consumption of energy during the lifetime was 20 kilowatt hour per kilogram of vehicle. So we considered the weight of 1 wheel, and then we calculated the energy that 1 wheel would be, well, that the consumption of energy would be associated to this weight of the wheel during the lifetime. So it would be 20 kilowatt hour per kilogram per kilometer. Yeah. No, through the lifetime, yes, for the 180,000 kilometers, yes.
Okay, well, thank you. Irene, I hope this answers your question, but if you need any clarification, just please ask. Okay, then we have a question from Carlos Carillo Galvez. Okay, but I see, okay, that later on you clarified this aspect through Jose's presentation, but another follow-up. Okay, are the eco-design strategies quantified from cost point of view in any of the projects presented? Okay, so just to read to all the speakers. For example, normally removable fixing are normally more expensive, screw versus weld, but if the product is finally recovered and repaired or recycled, part of this cost can return. So whoever wants to address this question or in order, just raise your hand, speak.
Well, I think that Victor has already answered the question, because at the end, in so many projects, the costs are included on the different calculations. In our case, for example, in MARBEL, the LCA assessment, life cycle assessment is in parallel performance on the life cycle cost assessment by monetizing more or less all these different energy material flows that are included on the LCA model are already specified from the cost point of view. And even when the different strategies are addressed, and when you have to even try to determine what are the costing profile of the different strategies, all that different all these different how can I say, externalizations or even indirect costs related to the implementation of the strategies are already included, because all these different scores that are have been stated by Violeta, when you have to apply this analytical hierarchy process, when you have been trying to determine what are the most prominent strategies, are already included on that. Okay, so in two ways: on the specification of the strategies by these different scores that are more or less could be probably a little bit abstract, but at the end of the project, by comparing with the help of the LCA and LCC methodologies, by the comparison of the different strategies and the finally solutions adopted.
I think I would like to add something more here, because I think we know.
Go ahead.
Somewhere. And I think he's also referring to, at the end of life, what can be recovered after. So yes, during the project, we can account for all the costs if we do LCA and LCC at the same time, as we do in MARBEL, COBRA, and Fatigue4Light as well. So in all the projects, we are considering also the cost part during the lifetime, but it's very difficult to consider what's going to happen after the first life of the battery. So in this case, we can do some assumptions, we can do some studies, we can also acquire some information from our partners that are giving us the information on the different demonstrators, as is the case of Picosa as well, and Carlos Carrillo from Picosa. So.
Okay. Now I see that Victor has also answered this question in the chat. Victor, do you want to comment something by voice?
Yeah, this is only to say that I fully agree with Jorge told and Violeta, and it's only to add to reinforce this idea. So it's very difficult to know what happened after the recycling, because the first point that we have to evaluate is the quality of the material is enough to reintroduce again in the value chain of the batteries. You know, this is the first step from my point of view. Yeah, it is easy. It is easier because if you consider that all material has a good quality, you can revenue and calculate this reduce of the cost in the value chain. But if this material is not enough in terms of the quality, maybe it can go to another processes, you know, for, I don't know, not for the battery, for the other kind of the processes to addresses these allocations in terms of the cost is very difficult to do in the life cycle assessments and the eco designs. And the other thing that I want to clarify, when I said in my answer in the chat that we don't have enough data, it doesn't mean that in our project we have data, you know, but this is particular data for a specific our case and the early stage of the project. It is not the industrial scale, so it is important to have more representative data in the end of life recycling stage and the repair of the processes, dismantling, in order to consider these aspects in the LCA studies. This is only, yeah.
Okay, thank you very much, Victor, for your comments. I'm a bit curious about the COBRA project, and I just want to ask you something. How close are we to having on the market cobalt-free lithium-ion batteries? Is this just I don't know, a desire for the future?
Yeah, as I mentioned during my presentation, the main challenge is to try to produce a cell battery with the same performance when we using cobalt. In the market, it's very, very early, and the technology is not maturity because we have to think that on the commercial stage, the cobalt is recycled. It's actually, I think, the main metal with its recycling. If we create a new generation of the batteries without cobalt, it is necessary to explore the new materials which are recovered. The yield of this material is enough in order in terms of the market to be recovered and compensate this is revenues. So that is my thought. But I don't know if Violeta wants to add something, because the life cycle costing is other for the, because EURECAT and IDEC has a strong relationship in this work, and we are doing the life cycle assessment from the environmental point of view in this project, and EURECAT is doing the life cycle costing in this. I don't know, Violeta, if you have some information. I can see you are in a lot of projects.
I'm here in representation of Fatigue4Light, so
Yeah.
let me change my hat for
Yeah.
COBRA. For the LCC in COBRA, I think what we can say for now, because it's not finished, but the data that we have is done on a laboratory level. So it's very difficult to compare and say, how is this going to actually, like, how is this going to behave when this reaches market level? For now, it's really like, it's a different evaluation on the life cycle costing side.
Yeah, but I have to remark that from my point of view, cobalt today, the recycling of the cobalt from the batteries, the yield is very reasonable, and from the environmental point of view on the market is very good, compared to the nickel, for example, or lithium, because it's more difficult to remove. More concerns is social aspect for the cobalt, because we have the geopolitical problems in these areas which it is extracted. This is the more, from my point of view, more concerns.
Okay, well, thank you to both of you, okay, for the interesting perspective you've given here. Okay, now I have some questions. Well, let's go to Jose. Jose, I have a question for you. So from my point of view, can you please share some thoughts on how do you ensure the environmental goals are met along with the technical requirements when you apply the eco-design methodology?
Well, it's not really easy to perform that. But I think that, for example, it's very necessary that you have tried to create a confident atmosphere with the different technological developers, because sometimes are people that are very involved in their work, and by treating some confident data or even restricted to confidentiality agreements, and it is hard to translate our interests in trying to perform some environmental analysis on the technological perspective. So trying to create such atmosphere to fix some different meetings, to try to solve the different questions arising, and at the end that this collaboration could be understood from the environmental and from the technical perspective. We have the same goal, that the project or the product will be successful. That will be my recommendations on that.
I have to say that I fully agree with you, because we've seen this also in the Fatigue4Light project in the consortium. A very good communication needs to be ensured, right, between the technical, let's say, or the industrial partners and the LCA team that needs data, or else you can't perform your work. So yeah, definitely.
Yeah.
Just another question for you. How do you ensure that eco-design and life cycle assessment methodologies are not static, but they evolve, with the advancement in technologies, with the changes in sustainability goals?
Are not what? Sorry, could you repeat?
How do you ensure, that eco-design and life cycle assessment methodologies, they're not static, but they evolve as sustainability goals evolve, also as advancement in technology occurs? How do you make these methodologies evolve at the same time?
It's really difficult, right, colleagues? Because I think that all of us, we have plenty of experience on that. Well, from the basis of this confidence and this atmosphere created on that, we have to understand that all the refinements that we could provide on the different assessments and all the refinements that we have with the intentions to acquire the more reliable data that will be implemented on the developments. The benefits from the technologies involved in the project, or even in the companies that are interested in the implementation of these assessments, will be even greater. At the end, our work, that for sure increases our expectations on our professional careers, is something that could be easily capitalized with the same companies. The different regulations that are coming from the European Commission, or even the necessity, the battery passport, the digital battery passport, for example, or the mandatory that is increased of the different companies by the implementation on the different regulations regarding the sustainability issues and the sustainability communication and dissemination on such perspective from the companies will help us, will help them or our assessment. So in that sense, the companies have to determine or even identify our efforts and our assessments with available, and this has to be even increased by this iterative process with the refinement of this data and the models and the results, right?
Okay. Well, thank you, Jose. I don't want to close the session without asking something from Aitor regarding the Liberty project. So just some thoughts here. Why is it important, Aitor, for the circularity indicator results to be proportional to the environmental indicator savings that you calculated through the LCA? Why is this proportionality important?
Yeah, thank you. So the idea with circularity, or what we have been seeing recently, is that circularity has become, I don't want to diminish it, but as a kind of a buzzword in terms of how to approach sustainability for different products, right? And also, and in the other hand, recently with the new European regulation for electric vehicle batteries, which is from this August, we've seen that a lot of the limits or the requirements that they have been stressing, they are more related to this circularity concept than actual environmental sustainability. So, for example, we'll have recycling minimums, and so recycled material minimums and recycled minimums after the life. So to put in the battery and to take out from the battery, so to say, in I think 2-3 years. So 2027, this will be starting, and then you will have strong limits in 2030, 2031. So this is going to be a reality for us. And they are circularity metrics, so to say. Then on the other hand, you will have a carbon footprint assessment mandatory for your battery as well. But this is, and that's why I also highlighted it, it's only one of the categories for the LCA. So it looks like circularity it's coming from maybe this buzzword thing I said, but it's going to be an adequate metric to measure if you are successful in your battery design or not, especially for sustainability. So now we need to be looking at the circularity metrics we've got and guarantee that those metrics really push for a more sustainable battery. And if they are not proportional, you maybe shouldn't be using them. And some regulations should be established whether this metric is good or not. So this was kind of this dichotomy between LCA and circularity. It's coming from this mindset. Also, let me just very fast answer something from way before regarding what Victor said about the quality of the recycled materials. Because in the work I presented, we assumed full quality of the materials, and we provided credits in this regard, which, of course, it's optimistic assumption, I'm going to say. However, as I defined, and Liberty also is thinking with a very technology-oriented mindset. So let's say technological, so state-of-the-art, maybe not, but market limitations were not considered at the moment. And especially with the cobalt, we know that cobalt is going to be recovered. And if it's necessary, it's going to be refined. But some other materials might not. This was not so much considered in the project. So we performed an optimistic LCA in terms of what is the best way to do things. And then, and coming back to the TCO or the life cycle costing thing, this in the project, in Liberty project, it's coming after the technology have been developed and researched, just to be coherent with what the stage of the technology is. We are developing new technology, then we'll see how it comes to the market. And this is a kind of a disclaimer I wanted to make, because I understand that the quality of the recycled materials, it's not here yet, but we're hoping it will be.
Fingers crossed. Let's hope for it. Yeah. Okay. I don't want to extend this discussion any longer, but if anybody from the audience has some follow-up questions, you can write to us, to any of the speakers, or to myself, and I will distribute the questions after the webinar at any point. Okay, so thank you very much for your attendance, for taking the time to listen to our presentations and learn more about our projects, and keep posted to other events that we will be doing in the future if you are interested in this specific area. Thank you very much for your assistance.
Thank you. Bye.
Thank you so much.
Thank you.
Bye.
Stay safe, everybody. Bye-bye.